Good morning. My name is Katie Picaron, and I work for Stacy Bent in the Department of Chemical Engineering. I'm working on the atomic layer deposition of manganese oxides as a catalyst for oxygen electrochemistry. And this is for the development of advanced catalysts. The reactions that we're working on catalyzing are the oxygen evolution reaction and the oxygen reduction reaction. And both of these reactions are important to many alternative energy applications such as fuel cells, metal air batteries, and as illustrated here, the photoelectrochemical splitting of water. And to help address many issues, nanostructuring helps to improve these catalysts and to coat nanostructured films. It's useful to be able to have a method to create highly conformal films. And that's where atomic layer deposition comes in. It's a vapor phase method that is capable of producing high-quality conformal thin films. And in my poster, I'm going to be discussing our recent work showing how we have successfully synthesized the films using atomic layer deposition. And these films have been shown to have good catalytic activity using a method capable of depositing highly conformal thin films. Thanks.
Stephanie. Our next speaker is Svenja Lohner.
Good morning. My name is Svenja Lohner. I'm a postdoc in Alfred Sporman's lab in the Department of Civil and Environmental Engineering. And the problem we're trying to solve with our project is that most of the transportation fuels and a lot of chemicals nowadays are derived from fossil fuels as primary energy sources. So the goal of our project, and the title of the project, is Bioelectrofuels Converting Electricity into Fuels, it should say, is to develop a novel energy conversion technology to develop carbon dioxide neutral hydrocarbons from electricity in a process called microbial electrosynthesis. In this process, we use a bioelectrochemical reactor to feed electricity into microorganisms in form of electrons. Together with atmospheric CO2, we can then generate biofuels and biofuel precursors with biocatalysts or organisms via CO2 fixation or CO2 reduction processes. And there are many biocatalysts out there that can do that, homocetogens, methanogens. Key challenges of this project is to find the optimal or a good biocatalyst, and also to elucidate the molecular mechanisms of this external electron transfer, which is thought to be the bottleneck of this technology. Our initial results show that actually there are a lot of biocatalysts that can take up electrons from electrodes, and there are many ways they can do that. So for example, we can use artificial electron shuttle compounds, or they can take up electrons directly from the electrode in biofilms. I'm happy to share all these results with you at the poster, and I'm looking forward to your comments and discussions then. Thank you.
Our next speaker is Zebo Chen.
All right, so my name is Zebo Chen. I work with Tom Jaramillo in the Department of Chemical Engineering here at Stanford. And I'll be talking at my poster about some of the work that we've done to develop forms of nanostructured molybdenum disulfide as a material that can produce hydrogen through electrocatalysis and also potentially through photoelectrochemistry. So I'll just motivate some of the work that we do by talking about the current status of our hydrogen economy. Like all the animations are gone here, but we have a pretty significant infrastructure for hydrogen right now. We produce about 65 million tons of it a year. This comes out of about 2% of our global energy consumption. And we make most of it through non-renewable sources of energy, such as steam methane reforming or coal gasification. And the reason we make so much is because we need it to make vast quantities of ammonia, for example, through the Haber-Bosch process, and also for in the petrochemical industry through hydrodesulfurization and hydrogenation reactions. There's some other applications as well. These are a smaller fraction of the hydrogen economy. Now, alternatively, you can use electrolysis, water electrolysis, to make your hydrogen. And the advantage here is that the hydrogen product that you get from water electrolysis is really pure, so you don't have the carbon monoxide byproduct that you have to take care of. which can be particularly problematic if you're going to be using the hydrogen in an ammonia synthesis facility, for example, where your catalysts are rapidly degraded by carbon monoxide, or in a fuel cell. Of course, you can feed in non-renewable sources of electricity into your electrolyzer. This is a little bit less interesting. We know how that works now. But more interesting is the fact that we can feed in renewable sources of energy into a water electrolyzer because it's just electrons. And here, you can actually start thinking about using electrolysis and hydrogen as a way to store energy from unstable power sources like solar or wind. So a third alternative is through photoelectrochemical reactions, and I'll be talking about how we think nanostructuring molybdenum disulfide makes it a very promising and non-precious material that can drive electrolysis as well as photoelectrochemical water splitting.
Our next speaker is Rahim Isfandiarpour. Rahim.
Hello everyone, my name is Rahim. I'm working with Professor McIntyre. So our project is about...
Other direction on the slides.
Oh, I'm sorry. What's that?
There you go.
Oh, okay. So our project is about the corrosion resistance anode, photoanode to produce hydrogen as a renewable source of energy by using, from the water splitting process by using light actually. So for this structure, where was the animations? Anyway. Okay, so what we are using is we are going to produce hydrogen as a renewable source of energy, and we improve the efficiency by minimizing the water oxidation steps. And from the other side, we are using silicon as the base of our electrodes, base of our anodes. So which is abundant, which is very common to be used in current solar technology, and also which has a low band gap, which can absorb most portion of the solar spectrum. So solar spectrum. So from the other side, we have TiO2, which is dimensionally stable. So this project actually is about the combination of the dimensional stability of the TiO2 and photoabsorption of the silicon, both of them for our anode. So the structure is like, we have our silicon as a substrate, and then on top of that, we have atomic layer deposition of TiO2, which is our corrosion resistance oxide, corrosion resistant canal oxide, and on top of that, we are covering that with a thin layer of iridium, which is our catalyst for water splitting process to produce hydrogen. So here you can see the results, the current density for actually pH 7, acidic, and also 1 molar NaOH. So we have low to moderate overpotential for all these environments, so which is a big step in this area. So in my poster, I will talk about more details of this project and other methods that we have used to improve the current density. Thank you.
Our next speaker is Andrea Medford. No, our next speaker is not Andrea. Andrew. My fault. It does say Andrew. And do we know how to find your slides?
I actually don't have a slide. I'm a very last minute addition, so I'm going to just give a talk.
Perfect. Thank you.
No
You know, all the
problem.
great speakers do it without visuals.
That's what I've been told, so. So yeah, my name is Andrew Medford, and I work for Professor Jens Norskov. My project is based on syngas conversion over molybdenum carbide catalyst. So as you all probably know, synthesis gas is a very important intermediate in the production of various chemicals as well as a lot of different fuels. So catalysis is central in both the production and the utilization of synthesis gas. So molybdenum carbide is a particularly interesting material because it's shown activity in various reactions including methane synthesis, methane reforming, Fischer-Tropsch synthesis, and higher alcohol synthesis. So what we want to do is use different tools in theory, such as density functional theory, thermodynamics, and kinetics, in order to place molybdenum carbide into the context of transition metals. And by putting molybdenum carbide into this context, we hope to be able to understand the origins of its activity and also understand how we can tune and improve the selectivity patterns of molybdenum carbide, and then ultimately design and engineer new carbide catalysts which are less expensive than the traditional noble metal catalysts which are used for a lot of these reactions. So if you're interested in hearing more about that and seeing some visuals that actually pertain to this, please come by my poster. I'd be glad to talk to you. Thanks.